I'm going to talk today about a study that we did with the spam sinkhole that's been running for a couple years, and we did some interesting joint analysis with routing and some botnet data. So I think we'll see some interesting things. I think I can blow through this because I think we all know quite a lot about spam, and we all have personal experience with it. But some of the things we're studying in this study relate to the third bullet down there, which is sort of investigating alternate ways in which we might want to develop spam filters. Of course, today predominant way of filtering spam is based on content, as we know that your mileage may vary with that. The other thing. So in this study, actually, what we're doing is studying some network-level properties of spammers to see if we can figure out some interesting things about where they're sending spam from and the types of techniques they're using based on network-level properties, not just on content. Of course, the sort of predominant network-level property that people use today to filter spam is IP address, and we all well, many of you who use Spam Assassin know that one of the checks that it performs is a DNS-based blacklist lookup in one or more blacklists. So some of the things that I'll be getting to in this talk relate to how well different spamming techniques evade listing and blacklist. Turns out some of the more devious techniques that I'm going to present are pretty darn good at it, staying away from blacklists. So before I get to the actual study, I just want to sort of present a little motivation for this talk. We've probably all experienced, some problems with our content-based filters. Where's my text? Maybe I am switching laptops. Why don't I do that? Here. Can I just do that?
Yeah, that's fine. Here, plug this in.
Yeah. To do this. Let's see what happens. Oh, we're back in action. I can't see anything. Now I can. Okay. So we've probably all experienced problems with our use of content-based filters, and I think the sort of main motivation for looking elsewhere and why we wanted to look at network-level properties is could we design better filters by looking at things like where the spam is coming from. Of course, as we all know, the problem with using filters that rely just on content is, well, you can do lots of fancy things. It's a fairly low-cost operation for spammers to do pretty simple things to evade fancy techniques. It's pretty low cost, for example, for a spammer to write a script that inserts, as we know, random garble into the content of an email. So you can go to great lengths designing Bayesian filters and doing lots of training, but it's fairly easy for each piece of spam to be customized to try to slip through your fancy tricks. And even if you've got everything just right, of course, you've got to constantly be tweaking these things. I don't know about you, but I'm constantly tweaking Spam Assassin rules and based on various things that show up in content, and that can be pretty annoying. Not to mention the problem with false positives. Of course, the other thing, and something that maybe people here are interested in even more than I am, is that, of course, by the time you're applying a lot of these content-based filters, it's too late, right? All this spam has already used up a fair bit of bandwidth. It's already been carried across the network, only to be just chucked or stored on taking up disk space somewhere at the other end. It would be nice if we could figure out something about where the spam is coming from, what techniques are being used, etc., so that if we could figure those types of properties out, well, maybe we could actually stop some of this garbage traffic closer to the where it's actually originating. So that would be nice. So that's kind of the motivation for why we started looking at these properties. our hypothesis is, which we haven't really arrived at yet, but I think some of the data in this study will be able to suggest that perhaps this approach may show promise. Is that, you know, our thinking is that if you filter based on, you know, some of these network level properties, if you can figure out some of the distinguishing characteristics, well then perhaps that would be a bit more robust. If you could figure out, you know, who the ISPs or ASs that tend to host a lot of the machines where the spam is originating, well, that might be a useful feature that you could incorporate. Something that's a little tricky, but that I'm actively working on now is you know, if you could figure out whether or not a machine is a member of a botnet, well, that would be very valuable information, of course. You know, if you see that same machine sending you an email, you know, that's probably something you'd like to know about. Some of the things we do look at in this study are, you know, where in the network, you know, is this spam originating in terms of IP address space, country, AS number, et cetera. And there is a paper actually that you can grab. There's a tech report. If you just Google for my name, you can just grab it right off the top of my web page there. So you can have a look at that. Of course, the challenge with doing this type of thing, if we want to design these kind of network level property filters based on network level properties, we need to figure out, you know, what are the most useful features for distinguishing the spam traffic from the legitimate mail. It's, you know, it's all well and good that, you know, most spam may originate from some part of the IP address space, but we need to figure out, you know, is that part of the space where the spam is coming from? Or is that, you know, originating more spam than legitimate email? And if so, then perhaps that's an interesting feature. If, you know, lots of legitimate mail and spam are coming from that space, maybe that's not so useful. So, as I said, we're not quite to the point of, you know, being able to write rules based on these properties, but this is just a preliminary look into some of these features. Despite the potential promise of this approach, to this point, very little, if anything, is known about these characteristics. And if you were at the last NANOG, you did see some, Randy gave a lightning talk on some of this work. So I noticed yesterday there was a reference to SuperNet hijacking. And just to, you know, not to present a spoiler before the end of the talk, but I will talk a little bit about that technique, which we did discover. So these are some of the properties that we're interested in looking at. I'm not going to look at all of them today. Just a little bit of a 30,000-foot view of course, what we found and what we're trying to look at. The spamming techniques, of course, are, you know, not surprisingly, a lot of the spam is coming from botnets. By our estimates, it's, you know, probably somewhere in the range of like 80 to 90%. Some of that is circumstantial, and I won't get into the details of how we did it, you know, all of our circumstantial evidence, but it'll be somewhat clear based on our collection techniques in just a minute. For example, we looked at things like operating systems of the machines sending spam. Lots of you know, Windows XP or Windows 2000 machines, etc. So, you know, yeah. So, and there's other circumstantial evidence that we gathered to suggest that a lot of the spam is coming from botnets that I'll get to in just a minute. Some of the techniques that we used are down there at the bottom of the slide. So one of the techniques we used to study some of the properties of spamming bots was to do a joint analysis with a trace we have of known Bobax victims. So the technique we used there was, I took another trace that someone else had gathered that was basically a command and control hijack, right? So now we've got PCAPs coming in from lots and lots of bots trying to contact a command and control that's been hijacked, and that gives us basically a hit list of lots and lots of IP addresses that we know to be bots. In particular, spamming bots, because this was a hijack of a Bobax drone botnet, which is exclusively used to send spam. So by doing that that intersection, we can now study like a smaller set of those machines that we know are botnets, that we know are bots. Right. So just to give you sort of an overview of the type of data that we collected before I get to some of the fireworks. The main data set that we're using is just a single sinkhole domain that's gotten about 10 million pieces of email since August 2004. The way that we built this sinkhole was by having an MX record a domain that had an MX record but never had a valid email address. It's surprising, you know, how much spam this has accumulated over the past couple of years. One thing we wanted to do, actually, because when we turned this sinkhole on, it was already getting tons and tons of spam. What we wanted to do actually is start from, you know, T0 essentially. So we started another experiment where we registered another domain and set up a similar kind of sinkhole where we're getting basically a baseline of 0 spam to start with, and watch kind of the ramp up in harvesting behavior. That kind of gives us a clean control, so we can sort of watch the ramp up a little bit. Something interesting that we're doing with that second domain, no super exciting results there yet, but the technique I think is kind of interesting, which is we've got a website associated with that domain, and then we have kind of a contact page that basically randomly generates some bogus emails. So we can see now who's crawling based on the web logs, and then later go back and see who's spamming those uniquely generated email addresses that, you know, a particular IP address crawled. So that allows us to do some correlation between, you know, who crawled the email addresses and who later spammed them. So we have some data there, but not enough to do, you know, interesting statistical things, just anecdotal things. It's amazing how hard it is to get spam to a domain when you actually want it discovered. The other interesting thing that we've done with this data collection is to instrument the mail server with a tool called Mail Avenger. So if you're curious in installing that tool, actually, it's a fantastic tool. It's not an MTA itself. It actually forks off to SendMail or Postfix or your favorite MTA. But what it does is it sits in front of the MTA and will do lots of other interesting things, like perform a lot of DNS blacklist lookups in real time, log them in an X-Avenger header. It will do passive OS fingerprinting. It will also do things like run a trace route back to the host that just tried to connect to you, for example. And you can do all sorts of customized things based on, you know, whether it just tried to hit a non-existent user or not, or things like that. So we instrumented the sinkhole with this tool called Mail Avenger, and then took a lot of active and passive measurements to see what was going on. The other thing we did is we logged BGP routes at the same network at which we were syncing the mail. So now we can see things like study reachability properties of, you know, those spamming machines at the time when we actually got that mail. And as we'll see, there's some pretty interesting things that turn up with that. So here's just sort of a picture of where we're doing this. We actually did this up in MIT's network. So yeah, so that's a picture of that. That's in the slides. You can go get that. Here's kind of an example of what the X-Avenger header looks like, and I've highlighted in a darker blue some of the more interesting features, right? So you get, of course, the relay IP, but you also get interesting things like, oh, what is the TCP SYN fingerprint? What's its best guess at, you know, using POF? Like, what is its best guess at the operating system? You can also you know, configure it to look up, as I mentioned, do DNS-based blacklist lookups in, you know, as many blacklists as you like, and it's right there in the header for later analysis. Something that's actually not in bold because we didn't actually use it for this study, but which could be potentially interesting at some point, is all these trace routes we've collected back to the mail relay at the time the mail was actually sent. So We use that actually for some interesting debugging things related to BGP that I'm not going to get into in this talk, but I'd be happy to talk about later. This is just sort of a baseline graph, some preliminary results. Just looking at on the x-axis, what we have is just the IP address space, bin by /24, and then we've got cumulative fraction of how much spam is coming from that bit of IP address space. And we've got this based on IP addresses, which is shown in the dark dotted blue line, and then by spam, total quantity of spam as well, which is sort of the cyan line there. Not surprising, you can go do some registry lookups and find that. So the way to read this is, steeper lines mean essentially more spam from that part of the IP address space, and not surprisingly, you can go look at some of these spaces and find things that are not very surprising. Lots of spam coming from APNIC allocated address space, cable modem space, etc. So there are a lot of things that you might expect. There are a few interesting things to note. This is actually a little bit of work in progress, and we're still working on the characteristics of the legitimate mail. So we're redoing some of that analysis now. But the red line shows a trace that we took off the Georgia Tech campus network, so IP address characteristics of all port 25 traffic. So actually that's that's slightly mislabeled because it's legitimate mail plus spam, because just everything coming off that link. So we're working on actually redoing some of that analysis. But it is interesting to note that there is a fair bit of legitimate mail coming in between 90 dot star and like 180 dot star, so where there's almost no spam coming from that space to our sinkhole. Okay, so first, one of the things we tried to figure out, of course, first of all, is how well are the existing kind of network level properties working for filtering, and I'll get to actually some specific measurements later. But one of the things we note is that, well, actually, this probably not conclusion is a little strong. Let me first describe to you what the result here is that we're showing. Basically, what we're doing here is asking the question, in our trace of a year and a half or what have you, how many times does a particular IP address show up in that trace? So if we see spam from a particular IP address, we count the number of times it shows up, and then that's basically what this is showing. And then the x-axis is a log plot. So you can see. Do I get a? Oh, there you are. So you can see, for example, if I go to 50% here, that roughly 50% of the IP addresses in the trace showed up, twice or fewer times. Now, keep in mind that this is a single sinkhole domain, so I think it's a bit of a strong conclusion to say that, this IP-based blacklisting is, not likely to be effective because, of course, what you're doing essentially with DNS-based blacklisting is collaborative across multiple domains. But as we'll see, there are still some shortcomings, and this is kind of interesting to note. I think it does emphasize the importance of using collaborating across multiple domains to build those blacklists, because the trend suggests that if you're just watching at any one domain, it's very unlikely that you're going to see well, in many cases, it's unlikely that you'll see that IP address show up again. Some bad actors based on IP to AS mappings that we perform. I don't think it's a big surprise, like some of the things we see at the top here. Although this again just sort of confirms a lot of the things that you've probably read and that we sort of read also in various articles about where the spam is coming from, and where there's some bad actors at the top. It's still probably interesting to note that a lot of this spam does appear to be coming still from U.S.-based networks. And I should emphasize that this is not, I would take these hard numbers with a grain of salt, because as we know, many of these networks are multinational corporations. So we just took primary country of the AS. There is a little bit of fudge factor there. Okay. This, I think, is sort of one of the more puzzling and perhaps shocking things that we found in the study. I'll credit Randy Bush with this cute term, BGP spectrum agility, and you'll see in a minute why he calls it that. Let me first describe to you what we saw here. So it's a little hard to see on this graph, but at this time, where my cursor is there, we see an announcement for a prefix. Then, shortly after the announcement for that prefix, we see spam from certain IP addresses, and oh, lo and behold, those IP addresses are contained in the route that was just announced. Okay, well, that's kind of interesting, but then, then you see, a couple more pieces of spam get sent, and then 10 minutes later, or a little less than 10 minutes later, things quiet down. And then, a little bit after that, you see the route go away. So basically what we're seeing here are very short-lived BGP route announcements interspersed with spam coming from the spaces, interspersed with the spam coming from those IP addresses contained in the space that's being announced over those short-lived times. It's hard to say, put an exact number on how much spam is being sent using this technique, but it's somewhere between maybe 1% and 10%. The reason I say it's hard to put an exact number, and where some of the things that people have been talking about yesterday, for example, with detecting route hijacks and things like that, may be quite interesting, is because it's hard for us to tell exactly, are we observing this particular technique that I just showed you, or am I observing a particularly noisy route coinciding with a part of the space that also happens to be sending a lot of spam? So there is some, if you sort of throw out, if you assume all correlation is causality, then you get up to about 10%. But it's hard to say that all of that is this technique. Certainly, this is a bit egregious, and we found one also that was quite a bit more egregious. These almost look like they're right on top of each other. In fact, they're separated by a minute or two. So you see announce, spam, withdrawal, repeat. Now you might be interested to know, like, well, what prefixes are these? I listed a couple of them on the previous slide, and as I mentioned, there were some that were fairly noisy that we were also seeing a lot of spam from, that we didn't see this kind of behavior. But a lot of these egregious patterns that we saw were /8s. And you might be wondering, like, what's that all about? And I guess some people probably remember from the lightning talk last time the explanation of this. And this is, I think, where Randy comes up with this term agility, right? So this is actually a really cute technique, right? So here's what these guys appear to be doing. You take a /8. It's actually not allocated to any one party. You've got a whole bunch of networks contained within that /8, but you've also got a bunch of space in there that's dark, that that no one's using, or that certainly no one is announcing. Sometimes we saw that it was completely unallocated, and other times we saw that it was allocated but not being announced. So then what happens is you see this /8 get announced, and that's actually, even though it's a big chunk of space, it's pretty stealthy, because all those guys that are announcing more specifics, can route traffic just as they were routing it. And now you've patched up all the dark space, right? And now you've basically lit up all this dark IP space all over the place inside that /8 that you can go hop around in. And that's exactly what we see. We basically see the space getting lit up, and then let me just go back to that. Each time we see the spam come, we see it coming from different IPs inside that /8. Of course, using such big prefixes too, like, gets rid of this pesky problem of, having your short routes filtered. It turns out that this agility technique is fairly effective at getting around blacklisting techniques. And I'll get to some of those results in just a minute. Here are some of the things that we saw from various characteristics of where these IP addresses were coming from in this space and characteristics of the reachability of these IP addresses at later times. For example, we went back at the time we did this study and we saw, okay, well, let's go look at these IP addresses and see, are they still reachable now? And not surprisingly, most of them are not. The other thing that I think is sort of important to emphasize is the utter strangeness of the AS paths we saw associated with some of these /8 prefixes. You would think that you could maybe look at this AS path and see, well, okay, let's look at the upstream provider and who's doing this kind of wacky behavior. Well, it turns out not so much, and whoever's doing this seems to be doing some very sophisticated things. It's very hard to tell where the reality of the AS path ends and the fantasy land begins. It's certainly clear that some funny business is going on because there are things like reserved AS numbers stashed in these AS paths, followed by things that famous players that are clearly probably not famous players. We should probably go back and check those trace routes and see where the mismatch is, but that's something that we haven't done yet. There's definitely a lot of funny business going on with those announcements. This is actually, I'll just blow through this very quickly because this is just a graph that you can go look at that shows how long these BGP announcement intervals are actually lasting, and this is for all the spam we saw, not just for these BGP agile senders. So you can see that this is basically showing that, okay, 10% of these spamming events are associated with these short-lived BGP route announcements. So again, it's hard to say to distinguish correlation from causality. So as I mentioned at the beginning of the talk, the other thing we did is actually to try to do some correlation with some of the other traces we have, where we identify IP addresses of known botnets, in particular known spamming botnets, to sort of see what are the characteristics of those spamming bots. I should emphasize now that actually what we're doing is taking a very small subset of our sinkhole traffic, because even though some of the evidence that we've collected, for example, the operating system characteristics, et cetera, suggests that most of our trace is due to spamming bots. What I'm going to show you now is only the stuff that we can verifiably say is coming from bots based on the intersection of these two traces, right? So I take my command and control hijacked IP addresses. I intersect that with the sinkhole from one domain, and now I'm going to get a pretty small set of IP addresses, but there's still enough there to look at. It's about 5,000 or 6,000 different hosts. So this is again a similar plot showing where the spam is coming from these spamming botnets, excuse me, and where in the IP address space these spamming bots actually are. Turns out in this particular piece of the address space in the mid-60s, there's proportionally less spam coming from bots. You might sort of wonder why that's the case. Seems to me that in that particular space, that's where other stuff is going on as well, like the BGP route hijack stuff that I showed you. This is sort of a rerun of some of the things, is something I showed you before with a slightly different x-axis. The question here that we're asking is, when we see a bot, one of these 5,000 or 6,000 bots that spam the sinkhole, how long is it before it comes back, or how long is it sticking around in the trace? So this is sort of a variant of the question of how many times does it come back. The main interesting thing to note here on this graph is sort of the intersect with the y-axis, which shows that about 65% of these bots from which we got spam at the sinkhole are only sending mail to the domain once. So again, that sort of suggests that there's a fair bit of transience in terms of the identities or the IP addresses. As I'll show you in a minute, when we look at the effectiveness of the DNS-based blacklists, the blacklists are a little more effective at capturing these botted spammers than they are at the BGP Agile senders, and I don't know exactly why that is, but it certainly seems to be that the collaborative spam filtering that comes as a result of doing this blacklist based lookups is a little more effective at catching these bots than it is at catching the agile senders. You might think, well, you see from this graph, for example, that there are a few bots, spamming bots, that hang around for a pretty long time. You know, if you look about halfway across the graph, because it's a log scale, that's like a day, and then you go a little bit further, and that's about 10 days. And you know, there's about 20% that sticks around, you know, for several months. And you might think, oh, maybe those spamming bots are particularly aggressive. Turns out, not so much. What we're seeing here is there's very little correlation between how long that IP address is sticking around in the trace and how much spam we get from it. So you might think that, oh, this guy's been around in the trace for 3 months. You know, maybe it's the case that that guy is sending hundreds or thousands of pieces of mail to your particular domain. And it turns out that doesn't appear to really be the case. That regardless of the persistence of any one of these IP addresses, the actual volume that we're seeing from any of these is pretty low. Okay. I realize I've put you through a lot of graph machinery, but this is sort of the last one that I think that you should really pay attention to. I think it's probably one of the more interesting pieces of data that we have in this study. And as I mentioned in the Avenger, in the mail Avenger traces, when we instrumented the sinkhole with Mail Avenger, what we did is perform blacklist lookups to 8 different blacklists. So, and then, of course, for each one of those pieces of spam, as we were receiving it, we were able to see at the time we got that piece of spam, how many different blacklists was that IP listed in? You know, was it listed in none of them or all 8 of them, right? And that's basically what we're showing here is like on the x-axis, that's how many different blacklists that IP address was listed in at the time we got the piece of spam, ranging from 0 to 8. And then the y-axis is the fraction of all spam that we received. So, and now I've broken this out. The red is for all spam that we got. The green is for the BGP Agile senders, and the blue is for the 5,000 or 6,000 Bobax drones and the known Bobax drones in the trace. So the way to read this, for example, is if I go up to 50% here, and I look at the green line, what that says is that 50% of the only about 50% of the BGP Agile senders were listed in more than 0 blacklists, right? So I'm sorry, 1 or more blacklists. So about half of them were not listed anywhere. Compare that to the blue line, and you see this point at 1 almost up to like 90 or 95%, and that suggests that of the spam that we got from these spamming Bobax drones, about 95% or 90% of those were listed in 1 or more of the blacklists that we looked up. So if you just sort of look down there at if you draw a line there, what the conclusion to take away there is that these BGP Agile senders tend to be listed less in blacklists than certainly on average, and perhaps perhaps also it suggests that some of these spamming bots are listed more than spammers using other types of techniques. Yes. Okay. So that's I think those are sort of the main fireworks, and I just wanted to conclude with a couple comments on that second sinkhole. This is a bit of a work in progress. We're still hoping for more spam, so if you could, there's some links somewhere on my page that somewhere reveal the identity of that sinkhole. So if you could link to us, that might help us get a little more spam. But just to see some of the things we're seeing at that, not entirely surprising, of course. We've all sort of seen these kind of phishing attacks. What we can do, though, is go back and now see, okay, well, we saw this phishing attack on a certain day. Who crawled those IP addresses that are, those email addresses that are getting phished? What we saw, actually, in this particular phishing attack, for example, is emails coming from two different IP addresses, clearly on the same network, but entirely different from the machine that actually crawled the email addresses from the web page. And not surprisingly, like all the Xmailer headers were totally forged. Like each one had essentially a different Xmailer. Okay, so I think I'd just like to close with just a couple of lessons. Some of these probably are not, you know, immediate, like anything we can do about immediately, but it's certainly the case that things like securing the Internet's routing infrastructure are a very, very critical piece of this puzzle. Just because we, you know, aside from content-based filters, the only thing that you know, that we're relying on as far as like network-level properties are IP addresses, and as we've seen from some of the techniques that I presented in this talk, IP address certainly isn't, you know, a particularly reliable indicator of, you know, of identity. So, you know, hammering down actually who's doing this actually, I think, is well, a prerequisite to doing that actually is, you know, probably better security for the Internet routing infrastructure. The other thing I think which deserves a little more attention is some of those distributions of spam across IP address space. So some of the things that we're intending to do now are sort of do a little better comparison of those distributions with the distributions of legitimate mail. So if we could see, for example, that certain spaces were more likely to be sending this spam, then we could use that as an interesting feature in developing these filters. And I think that may suggest that, and some of the results certainly also suggest that, you know, rather than focusing on individual IPs, focusing on aggregate network behavior like botnet membership or like region or you know, these types of aggregate behaviors may be more effective features to focus on. So that's it. That concludes my talk. Thanks for listening. Hope it was entertaining.